connecting so many nice people with excellent talks and absolutely excellent organization. And I think it's very difficult to organize it all over the world. So all over all the time zones. So I would talk about SAPT codes. Let me start with acknowledgement. The recent work was done for SAPT 2020 version with Krzysztof Szalewicz and Javier Garcia from University of Delaware, but our codes had many authors all over the years, so we managed to have this many contributions. And I would like to also thank my sponsors. Let me start with the basics. How can you calculate interaction energy for weak interacting systems? There are actually two basic approaches. One is supermolecular, when you calculate interaction energy by a subtraction of the energy of a supermolecule, for example, dimer, but it can be a larger collection of molecules, and you subtract energies of the monomers. Alternative approach is that you calculate interaction energy directly expanding it in power series. Both approaches have advantages and disadvantages. Supermolecular approach is very simple conceptually, so it's just a simple subtraction. You can explain it to everybody. It's universal, so any approach that can be used for molecules can be applied to supermolecular approach to calculate interaction energies of weak interactions. It can work better or worse, but it can be applied. So since you can directly apply methods for molecules, and there is a huge development of calculating molecules, you have very efficient codes, so you can use CCS DFT or DFT for molecules, and you get interaction energy for weak interactions. But there are a few disadvantages. This all relies on error cancellation. These interaction energies are very small. They are tiny compared to energies of the superstructures. So you must have some error cancellation. And it works usually fairly well, but not always. And you have something like basis set superposition error. So you have to deal with the basis set problem. You have to have identical basis set for the dimer and for the monomer. And also one disadvantage for interpretation is that you just get a single number. You have energy, but nothing, no physical interpretation. On the other hand, in the perturbative approach, it's basis set superposition error-free. You are more flexible with the basis set. And also you get not only total interaction energy, but also physical contributions. Well, it's the main disadvantage is that it's theoretically more involved. It's particularly due to symmetry forcing. It makes all the formulas more complicated and more difficult to program. So it's not as simple as supermolecular approach. So symmetry adapted perturbation theory is an example of this perturbative approach. You can call it SAPT or SAPT, and energy is obtained as Rayleigh-Schrödinger expansion of the interaction energy, but there are some distinct features. It's actually a triple expansion. You have expansion in the intermolecular operator, but you can also have optional expansion in the intramonomer operators. So these W's are differences between Hamiltonians for monomer A and B and fork operators for this monomer A and B. So you're essentially doing something like a Meller-Plesset expansion for the monomer. But this approach is not antisymmetric in the exchange between the monomers. This is not a problem with exchanges inside the monomers, but the problem is between the monomers, and you have to explicitly force the antisymmetry. So that's why it's called symmetry adapted perturbation theory. But then you get energy components. So in the first order, you get electrostatics, which is interaction between unperturbed monomers, Coulomb interaction between unperturbed monomers. You get exchange, which is a result of Pauli exclusion principle. Then you have induction, which is interaction of permanent multiple moments on one monomer with induced multiple moments on the other monomer. And exchange induction is an antisymmetry correction to this value. And finally, dispersion, which is a result of fluctuation, instantaneous multiple moments fluctuating and interacting with each other, and exchange dispersion correction due to antisymmetry. The problem with the SAPT, this historic, or well, it can be still used, but this wave function based SAPT, that it's fairly accurate or very accurate, but expensive. On the other hand, you have standard density functional theory, which is fairly fast, but cannot model dispersion. You can add empirically dispersion, but well, it's not going to be as accurate as ab initio method, and also it's not no longer ab initio. But actually, it turns out that most of the time in SAPT was used not in computing interaction part, but actually in computing correlation in the monomers. So the idea was to actually use DFT where it shines, where it can be used for calculating monomers. You have some implicit correlation within monomers. So the idea was to replace SCF for the monomers with DFT. With a few tricks that had to be solved, this method worked well. However, you had to use asymptotically corrected DFT functionals, which is not a problem, but standard ones do not work. And also use time-dependent DFT for dispersion. You can further improve that with density fitting. So you have large 2-electron integrals, and you can approximate them with 3-center integrals. And then you have all kinds of improvements, of all kinds of reductions. In contrast to other methods such as MP2, where you get significant improvement with prefactor, but the same scaling, in sub-DFT, actually, you have improvement in scaling with density fitting. So without density fitting, it's 6th power for dispersion, 5th power for transformation, but also kernel integral, time-dependent DFT kernel integral was also expensive. With density fitting, it's 1 order of magnitude better for hybrid functionals, and 2 orders scaling better for non-hybrid. The transformation is still 5th power, but faster 5th power than the regular version. And this integral is also faster, overall scaling 5th power. This traditional sub-DFT was applied to systems such as coroning dimer. However, recently we have greatly improved the code, so it can be used to systems more than 200 atom size. So that's the history of SAPT codes. The SAPT codes are unimaginatively labeled SAPT. It's because actually at the time there were no other implementations of this approach, of the symmetry adapted perturbation theory. So we still have the same name. It started in 1993. And in 2002, some improvements were published with first parallel version, first 3-body in model. In 2006, sub-DFT was added, also 3rd order SAPT for induction and dispersion. In 2008, density fitting version and three-body sub-DFT, and also high-spin open shell sub-DFT. In 2012, coupled cluster monomers could be used. It's a code from Tatiana Corona, which is very accurate, although this formal is pretty slow, only for small systems. And in 2006, we greatly improved dispersion. It breakthrough for going beyond 100 atoms. And finally, with a recent version, the whole code was rewritten. And also included was a package for potential energy surface. So the capabilities, the whole code was recently described in a JCP paper. It's free of charge. It's a non-commercial code. Source code is also available. You can tinker in it. However, it's not yet open source. Registration is required, but everybody is welcome for academic or commercial reasons. You can download it from this link, or you can Google SAPT 2020 and you get the same page. There are now a few other approaches for SAPT, other implementation, but our is the most complete SAPT and sub-DFT available, and it's also pretty competitive. You can do systems up to about 300 atoms and 10,000 basis functions. It works on multiple Unix platforms. We also try to have overall a wide range of compiler compatibility. And it's not only, it's a whole package, not only SAPT, but also other codes for asymptotic expansion. So you can get seamless connection with asymptotic. Also, this code for automatic potential energy surface fittings, also called AutoPES. It's a very time-consuming process to getting intermolecular potential force fields. So it helps to automate this problem, and can be used also with not only with SAPT. You can use it with supermolecular approaches. And finally, there is three-body code and open shell code. A few success stories for sub-DFT to convince you that this is the method for calculating small and medium range systems. It's not a complete overview. It's only a few systems I was working with. We started with a benzene dimer. We developed, it was actually the first non-test application of sub-DFT. We developed full potential energy surface for benzene dimer. And actually at the time it was believed that there are two minima for benzene dimer, slipped parallel and T-shape. And we actually found that the T-shaped is a saddle point, and actually the minimum is tilted. It has a significant effects on the spectrum. So this vibration is different compared to the regular T-shaped one. And also it's more stable than T-shaped. So it explains really a lot of problems, a lot of issues with the spectrum of this system. At the time also, sub-DFT was the only thing that could be used for potential energy surface, so we could get the minima, but if you have the geometry, you could obtain CCSD of T, and we compared these results with CCSD of T and also got fairly accurate results. We then improved this potential. We added third order induction. We also improved the fit, and with help of this new potential, we calculated the full vibration, rotation, tunneling spectrum for this system. There were some applications for molecular crystals. So on this picture, you see an RDX crystal, which is an overlap of experimental one and predicted from the scratch from ab initio calculations. So you can see some small tiny differences, but this is basically the same crystal. How you do it, you develop the potential, you do molecular packing. With the potential, you do energy minimization for some perspective structures. Then with the best ones, you do molecular dynamics. And this is what we got with our potential. We got structure with energy and density very close to the experiment. And it was the experimental structure. It had correct parameters, correct orientation, correct energy and density, and obviously also the space group. The only caveat is that we were a bit lucky. We estimated that there are some fairly significant three-body contributions. We didn't calculate them correctly. It's just an estimate. We didn't include them in the development of this potential. So basically the agreement between this and the experiment was actually slightly better than it should have been. There was some error cancellation between well, lack of non-additive contributions and not complete basis. What is interesting that we actually got better agreement that empirical potentials, well, empirical potentials that were fitted to get correct density and energy for these type of systems. So we get better results than experimental empirical potentials. Then there was a workshop in 2012 where it created another benchmark set. You must know a few benchmarks for intermolecular interactions like S22, S66, and others. Well, this benchmark was unique that it was first the geometry was given to participants, but the energies were not known. So the participants were asked to predict the energies as best as they can, but without knowing the answer. So you couldn't fit the DFT plus D method on those energies, and this is a more fair comparison of the method because those public S22, S66 benchmarks, they were frequently used as fitting set for methods. So SAPT DFT got second place for mean and sign error, mostly due to some, well, not perfect work on the repulsive wall, but by far the best medium % error, which is probably most important for doing intermolecular interactions. So it works for it long range. It also works very good for mid-range, for the minima, and fairly well for the repulsive wall. Finally, we got some improvements in the speed of this approach. In 2012, we redeveloped the algorithm. Actually, the formulas are completely equivalent to the original ones, but they were rewritten in such a way to program them efficiently. For non-hybrid functionals, the scaling is 4th power. With 200, 300 cystatom systems doable. And very recently, Javier and Krzysztof, they improved also exchange dispersion and other corrections, other terms. They are still a 5th power, but also doable within this regime. So also significant memory and disk space reduction. So these were the systems we tested them. It's not at the limit of the method, but it's where it starts to get well non-trivial. So Bucky catcher fullerene system, a model of molecular recognition, and also antibiotic with a peptide. So the timings in hours are, well, fairly modest. It's not a trivial calculation. You have to do some work. It takes a few tens of gigabytes, but not much more than that. And it's even for this 230 atom systems, it's doable within a week of one node 16 core system. So let me summarize. We have and we publish SAPT codes, which is the most complete implementation of symmetry adapted perturbation theory, both in the wave function based variant and SAPT-DFT. It's a complete package, not only that, but everything what you can need for intermolecular interactions, asymptotics, potential energy surface fitting, many-body SAPT approach. It's freely available. Everybody is welcome. We also help with some problems. And the SAPT-DFT method is, well, the best method for mid-range systems where CCS-DFT cannot be applied, and up to the limit of about 300 atoms with median error below 3%. And it's capable of systems of nano scale size. So thank you for your attention, and I'm open for questions.
Well, thank you very much, Rafal, for your very nice lecture. Now that your lecture is open for questions, and while the other participants gather them courage, I will probably fire up with my own questions first. As the SAPT methodology, can it be used for the excited states to calculate intermolecular interaction between, for example, molecule in excited state and other molecules in the ground state, or between molecules both in the excited state?
In principle, yes, there are some work on that, but it's very immature. First of all, you have open shell problems, and so also SAPT is not as mature for open shell systems as for closed shell ones. And there are also many other problems. I'm not fully an expert. There is a problem of Fermi continuum overlap between this stuff of, but there are some work. Konrad Patkowski published a paper 2 probably years ago doing some improve or going beyond our first high spin open shell case. So there is some work done, but it's still immature.
All right. Perhaps I'll have another question to you. Probably quite stupid, but you talk about computing intermolecular interactions, right, between two different molecules. Can you, with this methodology, evaluate intramolecular non-covalent interactions?
Well, I would like to say yes, but the problem is that you will have problems. You have to. The methodology requires you to separate something for well, 2 or more interacting systems. So if you have, if you have a systems that can be separated to 2 subsystems, and the Hartree-Fock or DFT for those parts will be reasonable compared to the whole one, so then yes, but this is something that probably will not work well for many systems where you want to do that.
Right. For example, in combination with fragment molecular orbital approaches or some kind of fragmentation methodologies, do you think it may work in principle?
It may work, however, this is only a few, only some work was done on local SAPT. So I didn't talk about it at all. It's there are some work with localized AO-based approach where you can actually approximate. So I think there may be a better hope with this approach, which is also pretty not that developed, and then you can divide it into fragments that will be calculated within this approach.
All right, right. Thank you. Thank you. I think Professor Choi has a question.
Thanks very much. It's a very nice talk.